Couple problems off the electron configuration worksheet. And in this worksheet, problem number 1 says, write the electron configurations for the following atoms. You can use the noble gas core if the atoms have atomic numbers greater than 11. So the first one is titanium. And when I look at titanium, titanium is Ti, and the atomic number there is 22. All right, so we have the 22. So that one's greater than 11. So I can actually write that with the noble gas core followed by the valence electrons to the outside. If I look at titanium, like I said, it's number 22, so it is a transition metal. It's located right here on the periodic table. Now, a couple ways I can do this. For the first one, I'll do this. For the second one, I won't. For titanium, let's fill up 22 electrons on this. So I start, and I'm going to use the diagonal diagram. I start up here at the number 1, and I put in my 1s electrons. So I have 1s, 2 up there. Once again, this is not using the noble gas core yet. I'm just doing the straight up one. So I keep following. The second place I go now, using my diagonal diagram, I have 2s2. That gives me 4 total electrons. I go to diagonal number 3 here. So this is going to be 2p, and remember there's 6 electrons in the p's if it's full, then 3s2. So now I'm up to 2, 4, 6, 12 electrons. Looking at how many electrons are in there. I still have another 10 to go. So I'm going to come over here to the 4 diagonal, and I get 3p6. And finally, I get the 4s2, but I still have 2 more electrons. So I clear out the 4s2s. And those 2 electrons, the d's can take 10, but I only have 2 left. So that gives me 3d2. Another way to fill this out would be using the periodic table. Remember, you go from left to right. So 1s includes all these on the top row, both of them. These are the 2 s's. That's 4 more electrons. I'm sorry, it's 2 more electrons. 1 electron there, 1 electron there. The p's can take 6. Then I go 3s, keeping with the periodic table, the 3 p's, the 4 s's, and I have to go 2 more over. That's inside the 2 d's. Now, if I want to write this as the noble gas core, what I do is identify where is it on the periodic table. It's right there. And here on the periodic table, right there, we look at the noble gas. That is going to be argon, Ar. So if I want to write titanium with the noble gas core, I start with argon, which, by the way, argon represents all this up through the 3p6. Now, what do I have left after the argon? I have the 2 electrons in the 4s and 2 more electrons into the 3d. So this would be 4s2, 3d2. By the way, how many valence electrons are there in this one? Anything outside the noble gas core. So we would say 4 in this one. All right? So here's the answer using the noble gas core. The one up above is still correct. It's just the expanded electron configuration. Now let's try rubidium. And when we look at rubidium, it is a little bit further down the periodic table. It is down here at 37. RB, we got 37. So we need 37 electrons on this one. So let's go ahead and erase what we had here on the periodic table. Listen, I'd just like to use the noble gas core on this one. So what I do is I identify where's rubidium on the periodic table. It's number 37. It's in the 5th row. It's right here. Well, this would be pretty easy. The noble gas is right here. I just have to identify which noble gas that is. It turns out for rubidium, the one on the row right above it is krypton, Kr. So for this one, I'd write Kr for krypton, indicate it's the core, and then 5s1. And that's it. That is absolutely it. You can use that diagonal diagram to go through it again, but what you'll find is that everything up through the 4p6 over here in the diagonal diagram, that would be krypton, and then there's one electron left over, that's in the 5s. All right. Now, going down to problem number 3 on this, says write out the electron configuration for the following elements and state how many unpaired electrons the element possesses. The one I picked was selenium. And for selenium, it is over here at number 34. So it is number 34 on the periodic table when we look at that. So it is going to be 34. There's in the 4s, it's right here. That's selenium. Now there's lots of ways to do this. You can do it off the periodic table, but this one wants us to give the electron configuration. And it does not say anything about using the noble gas core, so I'm going to have to write it out. 1s2, 2s2, once again using my diagonal diagram, 2p, 6, remember in the p's there's always 6, and then 3s2, 3p6, then 4s2, 3d10, and finally 4p. And how many electrons are there in that 4p? Well, there's only 4 left over. It would be 4p4. So now we have the p orbitals. To check the unpaired, let me just show you what happens in these p orbitals out here. This is the 4p orbitals. We have 4 electrons in there. So once again, electrons go in one at a time until each orbital has 1. And since there's 4 of them, we pair that one up. Now, how many unpaired electrons does selenium have? Listen, all the other ones and all the other orbitals before the 4p are all paired up. And we only have the 4p to worry about. So it turns out there are 2 represented by these 2 orbitals that only have 1 electron in them each. Those are your ones that are not paired up.